In previous sections, we went back and forth between, say, xy to polar r theta, or we went xyz and we had cylindrical and spherical coordinates. When we do this change of variables from, say, an xy or an xyz into another coordinate system, that's what we call a transformation, which is what we're going to be talking about in this section here. We're going to talk about these transformations. So for example, we have in the past gone from our xy to our r theta. Now recall that when we did this, we had to add in this r. In this section, we're going to find out why we had to add that r in. First thing I'd like to do is look at a general transformation from one set to another. So we're going to look at some generic set S, and we're going to look at some generic variables UV. In our case above, those generic UVs could be like an R theta. And then we're going to compare that to our rectangular region R in terms of X and Y. Let's say we want to do a transformation. So in general, a transformation will relate two sets of variables, X, Y, and UV. Remember, these are just variables. You can do an R theta or whatever you want. So that when you take the transformation, we're going to use capital T from transformation for transformation of the UV, whatever that is, to XY. Then we can write this as T transformation, where X is going to be a function of UV, Y is going to be a function of UV. Sometimes this is called a mapping, and we're going from S to our region R. The outcome is going to be this R, which is the transformation of S. R is called the image of S under the transformation T. So this is all just vocabulary. You're not going to be tested on any of this vocabulary. What I'd like to do is look at this example one. And we're going to look at this geometrically and see what's actually happening in a transformation. And then for the rest of this section, we're going to focus more on the algebra of it. So let's say that we're going to do a transformation from polar to rectangular coordinates. Our transformation is going to give an x value of r cosine theta and a y value of r sine theta. So you notice that x is a function of r theta, y is a function of r theta. Let's say that S is r theta, where r is going to go from 0 to 1, theta is going to go from 0 to pi over 2. So first of all, this is a coordinate system r theta. This coordinate system can be written as r theta. So this is my S, where my r values are going from 0 to 1. My theta values on the theta axis go from 0 to pi over 2. This is not to scale. So what this region looks like in our system S, or our set S, it looks like a rectangle. I'm going to call the piece from 0 to 1 A, and the piece from, well, actually, I'll just go around counterclockwise and look at each one of these line segments. So A, B, C, and D. And what I'm going to do is I'm going to take each one of these pieces. So A would be this line segment where R goes from 0 to 1, but the theta values are just 0. And I'm going to see what that looks like in my region R, which is X's and Y's. Again, this is just so you get an idea what a transformation does. We're only going to do this once, and then, well, maybe twice. And then we'll go ahead and stick to mainly algebra. Let's look at this piece A in my set S. So notice with A, the R values go from 0 to 1. My theta values on this first segment, line segment A, are 0. Look at my X and my Y values. Well, if R goes from 0 to 1 and theta is 0, X is R cosine theta. If theta is 0, cosine of 0 is 1. That means that my X is equal to my R value. And my Y value, if theta is 0, sine of 0 is 0. So my Y value is 0. If X is equal to the R value and R goes between 0 and 1, then my X values will also go from 0 to 1. And here my Y value is still 0. Which on my R graph would be a Y value of 0, but the X values go from 0 to 1. So that would be this line segment here. So that line segment A in my set S goes to a line segment in my XY coordinate system R. Okay. So this would be the transformation of that line segment A. Let's look at B. When I look at B, that would be this line segment where my R values are all equal to 1, but my theta values go from 0 to pi over 2. So let's look at what my X and my Y values are. If R is equal to 1, then X is going to be cosine of theta. And Y is going to be equal to sine of theta. Now think about that. X is cosine theta, Y is sine theta, and theta is going to go from 0 to pi over 2. That's the unit circle. Which means that, and I'm oh, that's not that bad. That would be, should have probably left it the way it was. This arc of a circle, so this would be the transformation of B. So we're taking this line segment and it turns into this curve in the XY plane. Right, so this is simply the unit circle. Now if we look at C, again we have a line segment where R is going from 0 to 1, but theta is equal to pi over 2. Which means my X value is 0 and my Y value is R. Which means my X value is 0 and my Y value goes from 0 to 1. And that would be this vertical line segment. X is 0, Y goes from 0 to 1. This would be the transformation of C. The last line segment is going to be this vertical line segment where R is equal to 0, but theta goes from 0 to pi over 2. And that would be D. If R is 0, then X and Y, they're both 0. So this is simply a point. It's the point 0, 0. And that's already on my graph R, so it kind of duplicated. So that just shows the transformation from polar to rectangular, which is why in rectangular, if we have a circle in our XY, when we change it to r theta coordinates, it's a lot nicer because although it doesn't look like it's a rectangular system with constant limits of integration, uh, that's because when we change from xy to r theta, our graph is still in xy form. In example 2, we have S, a generic S. It's the set UV. I know that U goes from 0 to 1 and V goes from 0 to 1. So this is a unit square in our UV plane. We want to find the image of S, so we want to get back to the R in the xy plane, given the transformation that x is equal to negative u and y is equal to negative v. So the first thing I'm going to do is I'm going to just do a sketch, even though it's not part of the problem, of S. So that would be this unit square. Remember, this is u and v. So I know that my u values are going to go from 0 to 1. So instead of taking each piece like we did in our previous example, I'm going to focus on the algebra here. If u goes between 0 to 1 and v is between 0 and 1, and I know that x is equal to negative u, that must mean that u is equal to negative x. So I could simply substitute negative x for my u value and then get rid of the negative by multiplying through by a negative 1, flipping the sign. I'm going to rewrite that as negative 1 less than or equal to x less than or equal to 0. So I have my x values. My v values go from 0 to 1, and I know that v is equal to negative y. So I'm going to do the same thing here. I'm going to replace v with negative y, multiply through by the negative 1, flip the signs, and so on. I have my y values go from negative 1 to 0. And this is also a unit square. But it's flipped around. Notice the shape has not changed from S to R. It's just sort of flipped around. This is a rotation of 180, well, is it 180? Yes, 180 degrees. So my transformation with respect to S is going to give me my region R. If I were to describe that set R, it would be the set of all points x and y such that x is greater than or equal to negative 1 less than 0, and y is negative 1 to 0. So we found the image of S, which is R, in the xy plane under that transformation. One more example. We want to find the image R in the xy plane of the region S. So S are all points u and v, so that u squared plus v squared is less than or equal to 1. And we're going to use the transformation that x is equal to 2u, y is equal to 4v. We're going to sketch R and S. First of all, let me look at S. u squared plus v squared less than or equal to 1 is a unit circle, but it includes the inner portion. So if this were my S, and I have a UV, I'll do a different color. That would be the unit circle. And it's less than or equal to, so it's going to include all this stuff here. I don't know what R looks like yet, but I do know that u squared plus v squared is less than or equal to 1. So I want to find R using this transformation. The transformation is that x is equal to 2u. So if x is equal to 2u, then u is equal to x over 2 squared plus y is equal to 4v, so v must be y over 4 squared. Getting rid of the parentheses, this is an x squared over 4 plus y squared over 16 less than or equal to 1. So if you recognize this, this is an ellipse. That's the outer part, the equal to 1 portion. But since it's a less than or equal to 1, then it's everything inside as well. When I graph R in the xy plane, I see that 4 is under the x squared, so that would be a 2 and a negative 2. And 16 is under the y squared, so that would be up 4 and down 4. And I have my ellipse, my sad ellipse, and everything on the inside of my ellipse. So we have taken the unit circle and we've transformed it to this ellipse. Now, if I was going to write out the transformation of S, it's going to be equal to the image R, where R is going to be all the set of all points X and Y, such that I can just write down x squared over 4 plus y squared over 16 is less than or equal to 1. And now this is just a note. Transformations are functions. And we have a property with functions that if a function is one-to-one, it has the property that if the y values are equal, then the corresponding x values have to be equal. And since transformations are functions, remember a function just says put something in, it'll do its job. It's a machine and something will come out. So you have an input and an output. Transformation does the same thing. You put in some set S and the output, the image, would be your set R. So when you do a transformation, it's one-to-one if, and here P and Q, these are points in S. So if you look at the transformation of points P and Q, if they're equal, then the corresponding points P and Q have to be equal under the transformation. So when we went back to example 1, we were going between the xy and the polar. That was not a one-to-one transformation because remember that point 0, 0? It showed up twice, right? There was a little bit of overlap. So one-to-one function, one-to-one transformation means there's no overlap at all. Everything is unique. It's what we call a unique mapping. So we had and remember that our transformation here, this is with respect to r and theta. So when r was 0 and theta was 0, and r is 0 and theta is pi over 2, in the transformation, those went to the same point 0, 0 in the xy plane. So remember, this transformed to the point 0, 0 with respect to x and y. But the r theta point 0, 0 and the r theta point 0 pi over 2, they're not the same, which means this transformation was not a one-to-one transformation. Now, on our next example, 2, where we just moved that unit square and rotated it, that is a one-to-one transformation. There was no overlap there. The next thing we're going to talk about is what we call a Jacobian determinant. So a Jacobian determinant of a transformation is like a scaling factor. Sometimes when you go from one set to another, you have to adjust it because the shape may change. So in that case, you may have this Jacobian that you need to add in. So let's look at what a Jacobian is. And this goes back to cross products. So a Jacobian is a determinant. If you're familiar with linear algebra or matrices, and you know what a determinant is. So we'll just call it the Jacobian determinant, where given any transformation, you can compute this Jacobian of uv by doing the partial derivative of xy over the partial derivative of uv. So what that means is since the x comes first, then the x's come first in the row. So it's going to be x with respect to uv, and the y is second, so it's going to be y second with respect to uv. When we compute this determinant, it's the cross product where you take your partial derivatives and multiply across, subtract, multiply across, which is what we have after the equal sign. It's the partial derivative of x with respect to u times the partial derivative of y with respect to v, subtract partial of x with respect to v times partial of y with respect to u. In example 4, we're going to just compute the Jacobian, and we have that x is equal to u plus v and y is equal to 2v. So we're going to compute the partial derivative of xy with respect to partial derivative of uv. Now the partial derivative, so the first entry is going to be the partial derivative of x with respect to u. So looking at x, the partial derivative with respect to u is simply 1, right? Because v is considered a constant. When you take the derivative, it's just 0. So that would be 1. The next thing we compute is the partial derivative of x with respect to v, which is 0 plus 1. So that would be 1. And then the next row would be the partial derivative of y with respect to first u and then v. So the partial derivative of y with respect to u is going to be 0. There's no u there. Sorry, I moved this. And then the partial derivative of y with respect to v is going to be 2. So here's our Jacobian. We're going to do cross multiplication. We're going to do 1 times 2, which is 2, minus 1 times 0 is just 0. And our Jacobian is 2. One more time. We're going to compute the Jacobian of r theta, where x is r cosine theta, y is r sine theta. So the Jacobian is going to be equal to the partial derivative of xy over the partial derivative of r theta. In our Jacobian, remember it's always going to be x with respect to r x with respect to theta. So if we look at x and we take the partial derivative of x with respect to r, cosine theta is a constant. So it is just cosine of theta. Partial derivative of x with respect to theta means r's constant. Cosine of theta, when we take the derivative, is going to be negative sine theta. So this becomes negative r sine of theta. Now we look at the partial derivative of y with respect to r, which is simply sine theta. Y with respect to theta becomes r cosine of theta. Remember, we're going to do our cross products. So multiply across, this becomes r cosine squared theta minus multiply. Minus a negative becomes a plus r sine theta, r sine squared theta, sorry. So notice if you factor out the r, you end up with cosine squared plus sine squared, which is just 1. So this Jacobian is r. So think of what I'm doing here. I'm going from r cosine theta, r sine theta. I'm going from polar to rectangular, xy. And that's where that r comes from, that Jacobian. Look down at this box here. We're going to look at the integral. So when you're integrating between the xy and some uv, what you're going to do is you're going to take that function in uv and you're going to multiply it by the absolute value of the Jacobian. So imagine if this S was a polar region, then the dA would be dr d theta. But the Jacobian was r, so that gives you your r dr d theta. In xy, this was dx dy. And that's where the r comes from. So why do we not have absolute values on the r when we do r dr d theta? And that comes from the way we define polar coordinates with multiple integrals. We said in the beginning that our r values would be positive. So that's why we don't have to worry about the absolute value of r. Example 6, we're going to go ahead and go through all these steps. We're going to evaluate our integral by first sketching the region R in the xy plane. We're going to compute the region S in the UV plane. We're going to compute the Jacobian, and then we're going to go from the xy to this UV by changing variables and evaluating the new integral. First thing I want to do is sketch R. My region R is x's between 0 and 2, and then my y values go from the line x to the line x plus 4. So let's see, x goes through x plus 4. This is going to be, oh, sorry, this is going to irritate me. This is going to be like a diamond. This would be y equal to x if it continued on, y equal to x plus 4. And then we'll pretend like this is 2 and this is 0. So we have our region R. That was A, part A. In part B, we want to compute the region S. Now it doesn't say that we have to sketch S. We just have to compute S. So I know that my x values are going to go from 0 to 2. And I know my y values are going to go from x to x plus 4. Notice that if I were to compute this integral the way it's written, I would have to have the y value limits of integration from x to x plus 4, and then the outer limits of integration would be the x values from 0 to 2, which I could do. That's not a big deal. So if x is equal to 2u, then I can just substitute 2u for this x value and get the 2u is between 0 and 2. So simply dividing out by 2, I get 0 less than or equal to u less than or equal to 1. And then when I look at my y values, I know that y is equal to 4v plus 2u. I also know that x is equal to 2u. So this inequality will be 2u for the x value. Y is 4b plus 2u less than or equal to x is 2u plus 4. Now when I look at this inequality, I see the 2u everywhere. So if I were to subtract 2u, I get 0 less than or equal to 4b less than or equal to 4. And then dividing out by 4, I have v values going from 0 to 1. Okay. So what I'm trying to do here now is find limits of integration for uv. I already have the limits of integration listed for xy. So now u goes from 0 to 1, v goes from 0 to 1. That would be my region S. It's going to be the set of uv such that u is between 0 and 1 and v is between 0 and 1, which is a nice square or rectangular region. When I compute the Jacobian of uv, remember that's the partial of xy over the partial uv. And I have my Jacobian, which would be 2, 0, 2, 4. Again, I'm just using the equation that x is equal to 2u, y is equal to 4v plus 2. And that would be 8 minus 0, which is simply 8. I found my Jacobian. In my integral that I'm going to set up for part D, so D says change variables and evaluate this new integral. Zero to 1. So the UVs both go from 0 to 1. My integrand originally was x squared, but x is equal to 2u, so it's going to be 2u squared. I have to switch everything from x's and y's to u's and v's. In parentheses, y is 4v plus 2u. And then the absolute value of the Jacobian, well, it's already a positive 8, so its absolute value is still going to be 8. And it really doesn't matter the order since I have two constant limits of integration. So I'll just go dv du. All right. Let's see. If I were to get rid of the parentheses and I could factor out 4 times 8, factor out a 2, so that would be a 64. I'm going to bring out 64. This is going to be a u squared times in parentheses 2v plus u, which would give me a 2vu squared plus u to the third, I believe, dv du. If I integrate with respect to v, first. Looks like it's going to be v squared over 2, so v squared u squared plus v u to the third, evaluating here from 0 to 1. And that just gives me u squared plus u to the third. Du. I have 64 u squared over 2 plus u to the fourth over 4. Oh, u to the third, sorry, over 3. Can't integrate. And again, that's a 0 and a 1. So 64 times 1/3 plus 1/4. Looks like that's going to be, I'm going to leave it as a fraction as 112 if I reduce over 3. Okay, so we did our transformation. Now, what you could do just for fun is to go back to the original integral and compare it to the integral from x values went from 0 to 2, y values, the lower was x, the upper was x plus 4 of x squared y dA. I would do a dy dx. If you compute this integral, you should get 112 over 3 because these integrals should equal the same value. We just did the transformation to simplify the limits of integration. This last example where we're in two-dimensional space gives us nothing. Well, not much. We have this double integral, and R is going to be this parallelogram bounded by these lines. It doesn't say to sketch it, but I'm going to go ahead and sketch the region. Okay, so y minus x is equal to 1. That's the same as y equal to x plus 1. And it's going to go up. The other one, y minus x equal 2, is y is equal to x plus 2. So these are, and this is not to scale. These are going to be two parallel lines. In the next one, y plus 2x equal to 0, that's going to be a line that passes through the origin with a very steep slope, -2. And then y plus 2x equal to 4 would be another, so sad. So it's this region here that I've shaded. And I'm not going to label these. I'm just looking at the sketch. It's not part of the question. Okay, the problem with this is that there are no constant limits of integration. If I look at my y and my x values, they will both have variables in them unless I break this region up. And this is an R region. Unless I break this region up into pieces, I'm kind of stuck. Plus, look at that integrand. That's hideous. So instead, what I'm going to do is I'm going to create a transformation. Notice I'm not given a transformation here. I have to figure out the transformation on my own. But what I do notice is that I have a y minus x and a y minus x. So y minus x equal to 1, y minus x equal to 2. Well, why don't I let u equal y minus x? Because then my u value is equal to 1 to a u value equal to 2. So u values go between 1 and 2. And then I have a y plus 2x, y plus 2x. So I'll just let v equal to y plus 2x. So my v value goes from 0 to 4. So now in my transformation, I have these nice constant limits of integration. I just have to find the Jacobian and then write everything from xy to my uv. So the problem with finding my Jacobian is I really don't have my transformation as x is equal to y is equal to. My transformation is written in terms of u and v so far. So the first thing I need to do is write x equal y equal so that I could take the partial derivatives of x and y with respect to u and v. Well, I notice that x is equal to y minus u. So now I have to get rid of the y so that x can be written in only in terms of u and v. However, if we look at the second equation, v equal to y plus 2x, and subtract 2x from both sides, I have y is equal to v minus 2x. Now I have one equation with x's, u's, and v. So if I add 2x, I get 3x is equal to v minus u. Simply dividing by 3 gives me x equal to 1/3 v minus 1/3 u. So now I have x equal to a function of u and v. When I look at my y, I can use either one of those equations. I could use y equal to u plus x. And I already found x. So y is equal to u plus 1/3 v minus 1/3 u. If I combine these u values, I get y equal to 1/3 v plus 2/3 u, which means I can now compute my Jacobian. Okay, so this will give me my Jacobian of uv. So remember, that's the partial of x with respect to u would be a negative 1/3. X with respect to v would be a positive 1/3. The partial of y with respect to u would be a positive 2/3. Y with respect to v would be a positive 1/3. Multiplying here, I get a negative 1/9 minus 2/9, which gives me a negative 3/9 or negative 1/3. So remember, in my integral, I always take the absolute value of my Jacobian. So the absolute value of my Jacobian is simply positive 1/3. And it's a constant. So when I set up my integral, I think I'm just going to pull that Jacobian out since it's just a constant. And I'm going to integrate. Let me go back to the integral. Y minus x, that's going to be my u. Y plus 2x is v, and then a plus 1. So this is going to be u over v plus 1 to the 4th power. Maybe I'll do u first. I'll put u as my inner integral. I don't think it matters, but I'm going to put v on the outside. So v went from 0 to 4. U was 1 to 2. This is going to be u over v plus 1 to the 4th. And I pulled my Jacobian out. I'm going to do du dv. So notice if I were to rewrite this, oops, this is 1 to 2. This is the same as v plus 1 to the negative 4. I'm going to kind of ignore that and do u to the 4. So notice that I was able to separate v and u. So I can treat the v plus 1 to the negative 4 as just some constant and ignore it. And then when I integrate with respect to u, it's going to be u to the 5th over 5. So again, I'm just going to ignore the v plus 1 to the negative 4. And I'm going to look at u to the 5 over 5, evaluated from 1 to 2. That would be 32 over 5 minus 1 over 5, so 31 over 5, which I am going to pull out because it's just a constant. And I'll look at the integral from 0 to 4 of v plus 1 to the negative 4. Would it be better if I wrote it as 1 over v plus 1? Nah, I could see that this is going to be v plus 1 to the negative 3 over negative 3. If you would like, you can do a substitution on the v plus 1. Just don't use u, because u is already being used. Use a different variable like w is equal to v plus 1. So if you had like a w to the negative 4, it would be w to the negative 3 over negative 3. And then the derivative is simply 1. This will be 31 over 15. This becomes v plus 1 to the negative 3 over negative 3. And I'm evaluating this from 0 to 4. I could pull the negative 1/3 out, but I'm going to leave it the way it is. This is going to be 4 plus 1. So it's 5 to the negative 3 over negative 3. Minus a negative would be a plus 1 to the negative 3 over 3. It became positive. And I'm going to just plug that in a calculator because this is getting a little bit too crazy. Let's see, 3844. Double check me on this. 5625. I didn't write this as a decimal. I wrote this as an exact fraction. But you might on your MyLab have to write it as a decimal. Let's move on to three-dimensional space. We're just in two-dimensional space. So let's say that we are in three-dimensional space with an x, a y, and a z, and we wanted to compute our Jacobian determinant. So in this case, the transformation is x as a function of UVW, y as a function of UVW, z as a function of UVW. So the Jacobian is the same. You have x, y, z, and these are partial derivatives, over UVW. So it's going to be x first, then y, then z, with respect to UVW, UVW, UVW. So how do we compute that? Again, going back to cross products in three-dimensional space with vectors, it's the same thing. If I look at this first partial derivative of x with respect to u, and I cover the row and I cover the column that goes with it, what's left over is going to be this determinant here. So what you took out, the partial derivative of x with respect to u, is going to be multiplied by the determinant of the partial derivative of y, of v, y of w, z of v, z of w. And then you can go ahead and look at the next one. Oh, just erase this whole thing. So going into the partial derivative of x with respect to v, that's down here. So remember the partial derivative of x with respect to u. Remember in your cross products in three-dimensional space, it's always a plus minus plus, which is why it's a positive, minus, or a negative, and then a positive. If you ignore the row and column, what's left over is going to be your cross product here. Partial of y with respect to u is partial of y with respect to w, and so on. So we look at our last partial of x with respect to w. And if we were to cover row column, what's left over would be that determinant here, partial of y with respect to u, and so on. So it's a little bit longer, but it's just computations. Example A, we're just going to compute the Jacobian. We're not going to apply this to an integral. Let's see, we have x is equal to v plus 2w, y is equal to u plus w, z is equal to negative 3u plus v. If I were to compute the Jacobian with respect to u, v, w, it's going to be 0, 1, 2, 1, 0, 1, negative 3, 1, 0. Let's see. So going back, it's a partial of x with respect to u, which is 0, partial of x with respect to v, which is 1, partial of x with respect to w, which is 2. So this is where I got the initial values, and now I'm going to use the formula below. This is going to be equal to 0 times the cross product doesn't really matter because I'm multiplying it by 0. So partial of x over partial of u times 0 minus 1 minus 1 times 0 plus 3 plus 2 times 1 minus 0. So this is gone. And I have negative 3 plus 2. The Jacobian is 1. So think about what this is. Remember, we're doing a transformation from one space to another. If the Jacobian turns out to be 1, then if I go from xyz to uvw, and I look at that integral, I don't have a scaling factor there since it's just 1. So that would be like that square we had in example 2, where all it did was kind of rotate around, but the shape didn't change. So basically, it's the same formula if you're doing a change of variables for a triple integral. If you have some x, y, z over region D, and you're going to look at this region S, where your functions are u, v, w, then you're looking at, remember, it's the absolute value of the Jacobian of u, v, w. And here, instead of some area, we're in three-dimensional space, so the region would be a volume. Before we do this last example, just for fun, you could see if you can figure out what the Jacobian is for spherical coordinates. Remember we had that rho squared sine phi in there, like we had that r with the r d theta. You could kind of verify where the rho squared sine phi comes from. It's a long computation, but it's kind of fun. Well, I think it's fun. Let's look at this last example. And we are going to use a change of variables to evaluate the integral. Our region D is bounded by these planes, y minus x is equal to 0, y minus x is 2, z minus y, and so on. Notice that I was not given the transformation, so I have to figure out my transformation. I'm going to do what I did with the previous example where I had to figure out a transformation. I'm going to notice that I have a y, oops, I don't want that one, I want the skinny one. I have a y minus x equal to 0 and a y minus x equal to 2. So I'm going to let u equal y minus x. So I know my u value is going to go from 0 to 2. And then I have z minus y, z minus y. V is going to be equal to z minus y. So v goes from 0 to 1. And then I have z equal to 0 and z equal to 3. Well, I'm just going to remember I need a uv. W is just going to be equal to z. So my w values are going to go from 0 to 3. I need my Jacobian, so I need to solve these equations for x, y, and z. Well, I know that x is equal to y minus u, and y is equal, I'll just go right down the row, is equal to z minus v. And I know that z is equal to w. So if I simply do a back substitution, I get that y is equal to w minus v. So z is written in terms of x, y, wait, z is written in terms of uvw, y is written in terms of uvw, and then I'll work my way back to x, which is equal to y, and y is equal to w minus v, and then I have a minus u. Okay, so now I have x, y, and z written in terms of u, v, w. The Jacobian of u, v, w is, when I look at my partial of x with respect to u, v, w, it's going to be -1, -1, 1. When I look at the partial derivative of y with respect to u, v, w, it's 0, -1, 1. Partial derivative of z with respect to u, v, w will be 0, 0, and 1. So plus minus plus. This is going to be a -1 times -1 minus 0 minus a -1, so it becomes a +1. 0 minus 0, so that's going to be gone. Plus 1 times 0 minus 0. So gone, gone. This is just equal to 1. I have my Jacobian is 1, which is good news because when I set up my integral, I don't have to worry about it. Okay, now my integral is x times y. Unfortunately, x is equal to w minus v minus u, and y is equal to w minus v. When I look at x and y, because I'm changing everything to uv, I have to multiply out w minus v minus u times w minus v, which would give me w squared minus vw minus vw plus v squared minus uw W plus UV. Maybe you guys got to check me on that. So if I combine my like terms, I have a W squared minus 2VW plus V squared minus UW plus UV. How nice. Okay, now let's set up our integral. So our integral, why don't I go du, dv, dw? They're all constant limits of integration. So if w is the outer, that was 0 to 3. V went from 0 to 1, and then 0 to 2 for u, with w squared minus 2vw plus v squared minus u w plus u v du dv dw. Ah, fun. Okay, so now it's just a matter of powering this all out. I'm integrating with respect to u, so I have a u w squared minus 2 u v w plus u v squared minus u squared over 2w plus u squared over 2v. I'm sure there was probably an easier way I could have done all this. And then 0 to 2 dv dw. If I plug in 2, that gives me 2w squared minus 4vw plus 2v squared minus 2w plus 2w plus 2v. And now integrating with respect to v, I have 2vw squared minus 4v squared over 2, so minus 2v squared w. 2v to the third over 3, so plus 2v to the third over 3 minus 2vw plus 2v squared over 2, so plus v squared. Okay. Let's see, putting in 1, I have 2w squared minus 2w plus 2/3 minus 2w plus 1. Oh, I don't know why this doesn't stay. So 2w squared minus 4w plus 5/3 would be 2w to the third over 3 minus 4w squared over 2, so 2w squared plus 5/3 w. Finally, I'll just plug in 3 in my calculator. 3 cubed over 3 minus 2 times 9 plus 5/3 times 3, and then we get the 0. Is this just equal to 5? Whew, double check my math on that. So that was just very tedious. And we're not going to do a lot of examples. That was actually our last example in 3-dimensional space because it's just more of what you had in 2-dimensional space. It's just a lot longer. So that's it for this section.